A spherical capacitor. The same too, but this is a sphere, two spheres. Inside a solid, outside is a shear, okay, with different radius, A and B. What do? We suppose the Q. Positive Q is inside, negative Q is outside. And we want to find the E inside anytime. For example, anytime. So we can make a Gaussian surface is a sphere co-center with these two shear. Okay. With this one, with the radius small r. Okay. And then see, we use the Gaussian surface. Okay, Gaussian surface. This phi is equal to EA. The reason is similar to previous. E is along the radius. Okay. So parallel to dA. dA is outward. Okay, dA. So E dot dA equal to EdA. So E is constant, take it out. And the integration is the total area. Okay, the sphere area, okay, is 4 pi r squared. And what is this? By a Gaussian surface, a Gauss law, this is a Q inside. Okay, so we found E. E is, you can see the E is proportional to 1 over r squared. Okay, the smaller r, the larger E. The larger r, the smaller E. Past integration, we have found a V between these two shear. Okay, we take along the radius. Okay, so we got V equal to, by definition, E dot dr. E is parallel to dr. So E dot dr equal to EdR, from positive to negative. Okay, equal to EdR. E is not constant, cannot take it out. So we put E inside, integration from R equal to A to R equal to B. That's a very simple calculation. Okay, we put a C inside and take the constant out. We get integration dr over r squared from A to B. This is very simple. The integration is minus 1 over r, right? So we get this, put AB, you get this number. We have V, we have a Q, and a Q over V, take this out, equal to 4 pi epsilon AB over B over R. You see the C is completely defined by its geometry, nothing to do with Q and V. Okay. And from this equation, we have a special case. There's just a sphere, a ball. Okay. Only one. Then we take another one is infinite. And sometimes we say, what is the capacity of this ball? Now, in that case, B is infinite. A B is infinity. This one we dropped. B and B cancel out. We get C. An isolate sphere. A equal to R. B approach 0. Positive sign. We get a C equal to 4 pi epsilon R. The C is a capacitor. Capacitance of this sphere. So that means again, a sphere, conducting sphere with radius r, has the capacitance C equal to 4 pi epsilon 0 r.
We'll use this electroscope and a large rotary capacitor to show how the voltage of a charged capacitor changes as the area of overlap between the plates changes. When we charge the capacitor by passing a spark to it from this charged rubber rod, the electroscope deflects, indicating the voltage on the capacitor. If we rotate the capacitor and decrease the overlap between the plates, what will happen to the deflection of the electroscope? The deflection increases, indicating an increased voltage on the capacitor. Rotating the plates back together to increase the overlap reduces the voltage to its former value.
Sample. In the figure 8, switch S is closed. To connect the uncharged capacitor of capacitance C 0.25 microfarad to the battery of the potential difference V 12 volt. The lower capacitor plate has thickness L 0.50 centimeter and face area A 2.0 times 10 to the minus 4 square meter, and it consists of copper, in which the density of conduction electron is 8.49 times 10 to the 28 electrons per cubic meter. From what depth deep within the plate must electrons move to the plate face as the capacitor becomes charged? Now, we see that one. How much Q you have? Q is CV. C is 0.25 times 10 to the minus 6. We have the unit standard Farad, not microfarad, Farad. Volt is 12 volt. So the Q is 3.0 times 10 to the minus 6 coulomb. This coulomb will move to the surface, okay? And we see how much electron you have, how much carriers you have. This is Q over E. E is electron charge, each one. So divide this one means altogether have this kind of a number of electrons accumulate on the surface, okay, the surface. And then we see that this total number equal to NAD. This is the area filled with carrier. The volume is AD. This is N is the number of carrier in copper per unit volume, per cubic meter. We know this one, we know A, we know D, we know this one, we can find the D. Okay, this is the answer we want to find it. Okay, this is N. Okay, this is N, right? This is given. This is A, 2.0 times 10 to the minus 4 meter. Okay, we use the standard unit. Okay, we find very thin, 1.1 times 10 to the minus 12. You see, this is picking meter. Sample. A storage capacitor on a random access memory RAM chips has a capacitance of 55 femtofarad. If the capacitor is charged to 5.3 volt, how many extra electrons are there on its negative plates? There's a capacitor, you have the capacitance, okay? The voltage, a very simple question, okay? Now, first, we know the number is equal to Q over E, okay? The Q is equal to CV, okay, all right? So we put the C is 55 femto, 10 to the minus 15 farad. V is 5.3 volt, and each electron has a charge of 1.60 times 10 to the minus 19 coulomb. So we get N. This is the answer. 1.8 million. Capacitors in parallel and in series. Capacitors in parallel, these three capacitors connect in parallel, and you can use an equivalent capacitor to replace them. And this formula is C equivalent capacitor equals sigma Ci. We have learned in high school, so I'm not going to repeat it. Capacitor in series, okay. These three capacitors connect in series in a circuit. We can use an equivalent capacitor, replace them, okay. And this number is 1 over C equivalent equal to sigma 1 over Ci. Sample. Capacitor 1 with C1 3.55 microfarad is charged to a potential V0 6.30 volt using 6.30 volt battery. The battery is then removed and the capacitor is connected in the figure to an uncharged capacitor C2 with C2 equal to 8.95 microfarad. When the switch is closed, charge flows between the capacitors. Find the charge on each capacitor when the equilibrium is reached. Now let's analyze it. When its equilibrium is reached, what happened? We have a Q, we have a V, we have a C. Q or V in this process, which one is constant? It has original voltage 6.0, 6.30. Well, connected is 6.30. Okay. Now, in the physics process, in this question, what is unchanged is the Q, the total Q unchanged, right? That total Q will redistribute between these two. By what standard? The standard is the potential of them equal because they connect in parallel. Now let me summarize. What is unchanged? The total Q before it closes and after the close is the same, just recontributed. What the standard? The standard is after recontributed, their voltage should be the same. This is physics. Based this physics, we say V1 equal to V2 equal to V. Q0 equal to Q1 plus Q2. That's it. Okay. And then we will that one. Q equal to C1V0. Q1 equal to C1V. Q2 equal to C12. This way are the same. Okay. Now we have this one, you get a V. Okay. This is the V. V equal to CV C1V0 over C1 plus C2. Then we get it. Okay. And then once we know the V, we can find the Q1. The Q1 equal to C1 over V to multiply V. Okay. And Q2 equal to C2 to V. This question is very simple, but it's very tricky. Remember that? In this process, total Q does not change. V changes. But the standard is the V1 equal to V2 in V finally. It's not V0, it's V, a new word, okay? That's the physics. Once you know the physics, mathematics is very simple.
We'll use these copper strips to hook these two identical capacitors together 3 different ways. For each hookup, we'll charge the capacitors to the same voltage with this dry cell, then discharge the capacitors through this ballistic galvanometer. The amount of deflection of the galvanometer will be proportional to the charge contained on the capacitors. Here is a single capacitor being charged. Here's the galvanometer reading from discharging the single capacitor. How will the reading change if we hook 2 capacitors in parallel and repeat the demonstration? The galvanometer reading is doubled. How will it change if we hook the 2 capacitors in series? Now the galvanometer reading is half that for a single capacitor.